morning and welcome to the third day of the International Winter School on Combustion. So this morning we have, we are going to do that change, right? Yeah. So today we are going to have a slight change in the schedule. Originally we had scheduled for Professor Seshadri's talks in the morning and Professor Ramsey's talks in the afternoon. But judging by the kind of questions and the interaction that Professor Ramsey received, he certainly needs a lot of free time with the students. So what we're thinking is that we will actually do Professor Seshadri in the morning before tea, and then we go with Professor Ramsey so that we have the lunch break for students to mob him, and then Professor Seshadri goes back again. And the last session will be, again, back to Professor Ramsey. So that's a slight change that we are making in the presentations today. So now we have Professor Seshadri talking about analytical methods and more in the fundamentals. It's my privilege to introduce Professor Seshadri to you. To the combustion community, of course, he doesn't require any introduction at all. But I always make it a point to read out a brief introduction of these experts as a motivation to younger generation. So Professor Seshadri is actually belongs to the Mechanical and Aeroengineering Department of the University of California at San Diego. He received his BE degree from the Coimbatore Institute of Technology in India in 1970, and his MS degree from the State University of New York at Stony Brook in 1973. And his PhD degree from the University of California, San Diego in 1977. After completing his PhD, he was a postdoctoral research staff member at Yale University, member of the technical staff at TRW, and assistant professor of mechanical engineering at the University of Southern California. He joined the UCSD faculty in 1982. The Professor Seshadri is an expert in combustion. He is interested in the chemical inhibition, the combustion of diesel fuels and solid propellants, the mechanisms involved in the formation of pollutants, and the destruction of toxic compounds. He has helped demonstrate the usefulness of asymptotic analysis in the science of combustion. Asymptotic analysis employs the mathematical concept of a limit to efficiently identify critical boundaries, reactions, and other factors dominant in complex nonlinear natural phenomena. In 1998, Seshadri applied an asymptotic analysis that succeeded in singling out the most critical interaction among hundreds ensuing when, let me read this, hundreds ensuing when industrial fire suppressant halon 1301 extinguishes a flame. Halon 1301 is widely used by the military to quench fires in planes, but the chemical, also known as bromotrifluoromethane or CF3BR, is no longer manufactured because it damages the Earth's protective ozone layer. Because Seshadri implicated bromine as critical to halon 1301's fire suppressing efficiency, and since bromine is the element in halon 1301 that destroys ozone, the work signaled that the search for alternatives should switch from naturally occurring elements towards development of non-toxic synthetic substances. Dr. Seshadri can speak about many combustion-related topics, including using fire to eliminate biochemical warfare agents. Professor Seshadri this morning.
Thank you very much, Satya, for the. Thank you very much for the very kind introduction. Today, on the topic of what I'm going to talk about today is the use of analytical methods to analyze problems in combustion. I'm particularly pleased to give this talk here in Chennai, because as it turns out, one of the earliest contributors to asymptotic methods was Srinivasan Ramanujan. You probably have heard of him. I'm sure he's a very famous mathematician. There's a book out on him. It's called The Man. How do we get that? Oh, here we go. So maybe I should just use this. Okay. So, well, this is a slight change. Okay, I shouldn't change. Okay, very good, yeah. He's of course from Chennai, University of Madras, Cambridge University. He's also the fellow of the Royal Society. And there's a book out on him. Sorry. He's often called the man who knew infinity, just because he had derived several asymptotic formulas. So as an example of some of the asymptotic formulas that he has derived, here are a few examples. The first one here is here. You can see that. Oops. So that's the first one is, okay, how do you turn the light? There's a pointer. Okay. Mm-hmm. Okay. The first one that you see here is an approximation of the logarithm, natural logarithm of the factorial of n star. It turns out that that's the asymptotic expansion. So for example, if you put a number 100, if there's 100 factorial, then if you can plug this up, plug 100 over here, and you put, this is a very simple formula that you see on the right-hand side. One can easily compute this, and that gives you an approximation for log of for logarithm of n factorial. Another very important asymptotic approximation is that of the quantity pi. So here you see the asymptotic. In fact, this approximation is currently used in many of the fastest algorithms that those are currently used to calculate pi in computer programs, for example. Now, what you see here is that this is an expansion in the value k. So there's a leading order term, and the leading order term is when you put k equals 0, you get the leading order, and then you add additional terms, then you get the first order correction, second order correction, and so on. So what I have done is I actually did compute the 0th order term here, and I wanted to show you that the 0th order term, it turns out that the 0th order term is something like this. 3.14, 159, okay, 265. So this is what you compute, the 0th order term. Now it turns out that the actual expansion for pi is a 3.14, 159, 273, and so on. So you can see that the 0th order terms are already accurate to the first 6 decimal digit. So now once you add the first order correction to this, then it turns out it will be accurate to another 8 decimal digits. So that's the power of this method of this asymptotic approximation. And I didn't have the patience to compute the first order correction, because the next term was of the order 10 to the power of minus 6. So that was too complicated, or too difficult to add on to this. But nevertheless, you can see how accurate the approximation is. So often in the fastest computer programs, it's often sufficient just to go to the leading order term and the first order correction. And here's another very interesting asymptotic approximation. This is for the partition function for the number n. So what is a partition function? A partition, so the n is an integer. A partition function is defined as the number of ways you can partition the number 4, for example. The number 4 can be written in 5 different ways. I mean, you can write the number 4 as you can do that just 4 by itself. Okay. 4 by itself. You can write that as 3 plus 1. Or you can write that as 2 plus 1. Okay. So you got 2 plus 1 plus 1 plus 1. Then you got 1 plus 1 plus 1. So you can see that you have 5 different ways to partition this number 5. Okay. So actually, I computed so I plugged in 5 here, plugged in 4 here, and I got the number 6 as an answer. So you can see that so you can see it's off by a factor about 16% off. But it turns out that when it says that n tends to infinity, so it's actually accurate only for large values of n. So it turned out that someone has actually computed the partition for the integer 200. So by the way, when this was discovered, some person took the time, almost a month, to calculate the partition of 200, which was an extremely large number, and then they computed using this formula, and it was accurate to about 0.04%. So that was how accurate it was to. So you can see that accuracy of this approximation improves as n becomes larger and larger. So that's, you can see all the aspects of asymptotic analysis right there. There's a leading order term and a correction, and if you add more and more correction to it, it gets better approximation. And here you can see another example of a partition function which is only whose value approaches the true value as n tends to infinity. So by the way, he has actually derived literally hundreds of asymptotic approximations of this type, and some of them are still being proved, and some of them already in use. So that's the introduction I want to give to asymptotic. So that's what I'm going to try to attempt to do here, is to try for combustion problems, for example, try to get an asymptotic approximation, for example, burning velocities or the critical conditions of extinction, and get analytical expressions, and try to then compare how the analytical expression compares with what's obtained from detailed numerical calculations. So that's what the goal of this presentation is today. And often there's a question about, is asymptotic method still useful, because one can almost compute these things by the electronic computer. And I'd like to convince you by the end of the session, the asymptotic methods are indeed useful because they offer an enormous understanding of the physics of the process. So okay, so what I'm going to cover today is I'm going to start out with some very simple examples of asymptotic approximations. This is the outline of my presentation. The introduction, by way of introduction, I want to talk to you about asymptotic analysis of non-reacting flows. And this is something many of you would be familiar with already. I'm going to illustrate how asymptotic methods are used to solve problems in fluid mechanics, in particularly boundary layer theory. Then I will move on to describe the role of asymptotic analysis in heat transfer. So as you see, that this particular aspect only involves the mass conservation equation and the momentum conservation equation. And then we look at the role of asymptotic analysis in heat transfer. We add on the energy conservation equation. And then, of course, when we look at problems in combustion, you also have the more additional equations, mainly the species balance equations as well. So we're going to start out again very simple. This is the asymptotic analysis of thermal explosions. And some of this Professor Ramsey actually covered yesterday. So I'm going to do the same problem, look at the same problem, except by looking at asymptotic methods. Then I will move on to asymptotic analysis of non-thermal ignition. Again, this is something which Professor Ramsey talked about yesterday. As an example, we're going to look at hydrogen-oxygen system ignition. This non-thermal, because the temperature rise will be presumed to be small during the ignition period. And then I'm going to move on to asymptotic analysis of a continuously stirred flow reactor. This is a classic problem that many chemical engineers look at. Basically, the CSTR. So that's going to be my presentation today. Okay. All right. So what's asymptotic analysis? In asymptotic analysis, it has various aspects. There are various aspects to the asymptotic analysis. It is actually an approximate solution to the describing equations. And you see this procedure is as follows. The first thing one needs to do is non-dimensionalize the describing equations. So that implies that you have to select characteristic scales, often a length scale or a time scale, and for the independent variables, and some characteristic scales also for the dependent variables. Okay. So when the equations are non-dimensionalized, the next is to look for that several parameters will appear. For example, in fluid mechanics, you will see that there's a Reynolds number and a proof number that appears in the analysis. And then one looks for limiting solutions in the limit of large or small values of those non-dimensional parameters that appear in the equation. Again, so this is what I want to illustrate today. And then, so once you look at these limiting values, then you get, then the equations become simpler, and one can solve those equations using analytical methods. And what it does in combustion theory, it improves understanding of the processes and provides simplified equations for use in computations. Okay. Okay, so and Professor Williams talked about this yesterday, so I'm just going to outline it again. For reactive flows, one needs to integrate the following set of equations. There's, of course, the mass conservation equation, and there's momentum conservation, which is the equation of motion. So this is for fluid mechanics. Then then one adds on the energy conservation equation, which is, of course, derived from the first law of thermodynamics. Then you have the species balance equation. So if you have n species, there are n equations, species balance equation that one gets. Of course, when you add up all the species balance equation, you get back the mass conservation equation. So therefore, that's actually n minus 1 independent species conservation equation that one can write. And now the source terms for this species conservation equation, that input for that comes from chemical kinetics, as you see here. So one needs to have knowledge of chemistry. In addition to all this, in the species balance equation, the diffusion velocity appears. So therefore, now you need n. Then you need diffusion equations here as well, and then finally the equation of state. So if you add up all that, one has like 2n plus 4 equations, and it's nearly impossible to simultaneously integrate all these 2n plus 1 equations. Even the fastest computers cannot do that. So therefore, it's necessary for us to have to get approximate solutions to these set of equations. So that's what I'm going to talk about today. Okay, now here I've listed, so here are the equations. We have asymptotic analysis of non-reacting flows, basically fluid mechanics. Here is the mass conservation equation, the equation of motion. So it's in the form of, so this is actually mass times acceleration. It's balanced by the forces. I can see the pressure force, the viscous forces, and the body forces. So basically it's F equals ma, mass times acceleration equals the forces on the right-hand side. And this is the thermal energy equation here. Now again, it's derived from the first law of thermodynamics. So that's the change in enthalpy that you see here, and it's balanced by the heat added plus the flow work term. There's another term that appears, and that is the viscous dissipation term. And the viscous dissipation term is the conversion of irreversible conversion of mechanical energy to thermal energy. So that's what this term. So this term will always turn out to be positive because it's an irreversible process, mechanical to thermal energy. Okay, here the variables: rho is the density, t is the time, w bar is the velocity, the p is the mechanical pressure, t is the temperature. Tau is, of course, the shear stress tensor, and F is the body force per unit mass. And these are the properties: the viscosity, the heat capacity, and the heat flux vector. Now, this quantity that appears here, beta, is given by this expression here, is actually the partial log of rho versus partial log of t. So for a perfect gas, if you assume that the gas is ideal, then this quantity beta turns out to be minus 1. So it's actually, sorry, 1. So this term here is minus 1. So therefore, since there's a minus in front, beta is actually 1. So that's so that appears on the right-hand side here. So you can immediately notice that if you assume that the flow, if you make a constant density approximation, then immediately you can see that these terms will drop on the right-hand side. Okay. So for this particular presentation, I'm going to restrict my attention to body forces due to gravity. And here that's the body force due to gravity. Ng is the unit vector in the direction of the gravitational force, and g is the magnitude. So therefore, you can see that's F body force per unit mass. And if we want to neglect radiation, and of course, as Professor Williams talked about yesterday, for reacting flows, there are several other terms that appear on the right-hand side. Since we are concerned here with non-reacting flows, there's only one term, and of course, I have also neglected radiation. Therefore, there's only one term as far as the heat flux vector. And as you can see, this is given by the Fourier's heat conduction law. The heat flux is proportional to the gradient of temperature, with the constant of proportionality being the thermal conductivity. The viscous dissipation term is given by this expression, and this is the term that appears, is actually the one right here. You can see that these are all squares, so it turns out this quantity F5V, this is always positive, with they're all squares that appear. And it turns, I can easily show that all this quantity is actually greater than this here, so therefore this always turns out to be positive. Okay, so that's the, all right, so those are the set of equations. Now we're going to go ahead and try to non-dimensionalize this set of equations. And you can see that, so as I said, the first step is to select proper length scale and the velocity scale, and of course a reference pressure. So the selection of these scales is crucial, and how do you select them? And usually the physics of the problem will suggest how to select these quantities: L, reference pressure, a reference velocity, a reference temperature, as well as a reference temperature difference. As you know that in problems of heat transfer often almost always involve temperature differences. So therefore, if you have a problem in heat transfer, it's almost always possible to identify a reference temperature difference. As well as in a problem of heat transfer, one can always define a reference temperature and a reference temperature difference. So so again, I want to emphasize that selection of these, how do you select these quantities depends on the problem you're looking at, okay? And it turns out that often, any physical problem, it's always possible to get these quantities. Right. And often they're selected, these quantities are selected so as to make, the idea is, for example, you select a value of u infinity such that the velocity is of order unity. So we try to select these characteristic properties such that the dependent and the independent variables we are looking at, they're all of order unity. Okay. All right. So here's so I've now written the equations in the dimensionless form. That's the mass conservation equation. And here is the equation of motion. And you have, again, you have seen this before. So I just want to show this equation in the complete form. This is, of course, a Nabla operator, non-dimensional operator, non-dimensionalized with respect to the characteristic length. That's what the equation that appears. Now, you notice that there are two terms that appear in this equation. One is the Reynolds number, which is given by this expression, and the Proust number that appears. So there are two non-dimensional numbers that appear. So the equation of motion is completely governed by just the Reynolds number and the Proust number. Okay. Now, so now you recall that we still haven't selected. There is a reference pressure, and we can select the reference pressure whatever we want here. So now you can see that one way to select the reference pressure is to select it such that this particular expression is satisfied. So this is again a hydrostatic component. So this is the hydrostatic pressure that one obtains from this equation. So one can select the reference pressure such that this particular expression is valid. So this equation again tells you how to select the reference pressure. So once you do that, that's the resulting equation after having selected the reference pressure in that particular fashion. Okay. Again, you notice that if you look at a constant density flow, if you assume that the density is constant, then this quantity rho star is unity. So therefore, this particular term drops out here. So then you just have a balance between. So that particular term drops out. That's all you have here. This particular expression. All right. Okay, so that's what I've done here. Let me say a few more things here. So okay, so for simplicity, I've now assumed constant density. So rho star is 1, mu star is 1. All these quantities are unity with the constant density approximation, and also the properties are constant, the viscosity. So we neglect the changes in values of the viscosity with respect to temperature. So that's the resulting equation. That's the that's the momentum conservation equation. Now this quantity here, epsilon, that appears here, is simply, for example, this. So the 1 over Reynolds number, you can see that this particular term drops when rho star is 1. We have just this equation. And I've defined, there's only one parameter in this equation now, and that's the Reynolds number. So we define define a quantity epsilon, which is 1 over the Reynolds number. So now you can look, if you look at this particular equation, there are second derivative terms here. So therefore, in principle, if you write the velocity in its component form, u, v, and w, then in principle you need 6 boundary conditions to be able to solve this equation, this particular equation. So you need to apply 6 boundary conditions. Now here, something very interesting happens. If one assumes that, if you look at an inviscid flow, that means if one drops the viscous terms, then for the inviscid flow, you can see that this equation, one obtains this equation, and a very interesting, which is the Euler's equation. And one interesting thing that you observe here is that the order of this equation has been reduced. There's only now a first derivative in velocity. So therefore, this can satisfy only 6 boundary conditions, whereas this particular equation can satisfy, one can apply 6 boundary conditions here, but this has only 3. So you can see that the order of the equation has been reduced if one neglects the viscous terms. Okay, now let's see, so what kind of asymptotic approximations that we can make. If one takes the limit of large epsilon, that implies that the Reynolds number is very small. Okay, if Reynolds number is small, then you get this large epsilon. Okay, which is a large epsilon. Then you can see that if epsilon is large, then one can neglect this the convective terms on the left-hand side, and now you have a balance between the viscous terms and the pressure gradient. So this is a balance. This term drops for large values of epsilon, and that's the classical lubrication theory. And of course, and not only that, so that's the leading order equation is just going to be the balance between these terms, and one can actually have corrections to that. The corrections, so one can perturb the velocity, and that would be the correction terms, and that is the classical, what's known as regular perturbation expansion. So in the regular perturbation expansion, the order of the equation is still maintained, and then one actually perturbs the velocity, and each term is of the order 1 over Reynolds number. So that's one. So it turns out it's a regular perturbation expansion. Okay, so that's, and of course, if you take the leading order term, if you have a flow in a pipe flow, so this will give you the classical the parabolic profile for the pipe flow problem here. Okay, now this is the more interesting one, which is the limit of epsilon tending to 0, and which is what is boundary layer theory. Now, for small values of epsilon, one can actually, as you can see, one can to the leading order, one can drop this. But then but there is a problem when this term is dropped, because recall that this particular equation is constrained to satisfy 6 boundary conditions. So if you drop this particular term, the order of the equation has been reduced, and that particular equation can only satisfy 3 boundary conditions as opposed to 6 boundary conditions. And so therefore now the problem becomes singular. So it's the order of the momentum equation is no longer maintained. So therefore this is what is the classical singular perturbation problem, and which is of course the central basis of asymptotic theory. And in the singular perturbation problems, they will appear a thin layer. There will be a thin layer, and in this thin layer, one should now one should rewrite this equation such that epsilon no longer appears, and then solve the set of equations in the thin layer and then match it. So basically the way the singular perturbation problems are done is the leading order, so one assumes that epsilon is small, drops that term, solves the set of equations, then you get the velocity profile, which is called the outer zone, and then rescale the momentum conservation equation such that epsilon disappears in this equation, and then of course that would allow you to satisfy the other three sets of boundary conditions that was missed, and then one does applies appropriate matching conditions for the. So that's the approach here. Yeah. Okay. Okay, so now I'm going to look at the very classic boundary layer problem, which almost all of you may have looked at in the past, and try to illustrate the asymptotic aspects of the classical problem that you've already looked at. And that is, mainly I'm going to look at the classical problem, which is the boundary layer theory applied to two-dimensional flow over the surface. So essentially, what I'm going to look at, I'm going to draw the picture here. So this is what we want to look at. So assume that's a flat, so it's a flow of a flat plate. The flow comes in this direction. Then you have the semi-infinite flat plate, and there's you got to show there's a thin boundary layer. The thickness of, so this is a x in this direction. That's y, and this is the u component of the flow velocity, and that's v. This is a u infinity, so therefore in the non-dimensional quantity, u is going to be 1 over here. U is 1. So this is so there's a boundary layer, and if you want to plot the velocity profile, get something like this. This is u equals 1. It goes from 0 to 1. So that's the problem I'm going to look at. Okay. So we are looking at the limit of okay, yeah. So again, I'm looking at this equation. I'm trying to look at this equation in the limit of epsilon going to 0. So then, in the limit of epsilon going to 0, then as I said, then classically you get a boundary layer flow, and this part in this region, so there is a thin boundary layer of thickness of order delta. And this is so in this region, the Euler's equations apply. And the boundary layer equations are valid in this particular way. And this is that's the velocity profile. Yeah. Okay. All right. And I'm sure you've seen this in many in the fluid mechanics textbooks. So so this is the equation this is the equation of motion. In the for u, the u component of the flow velocity, which is written here, that's the equation of motion. The epsilon and v is of course the normal component. Now it turns out from this analysis one can show that there is the boundary layer that grows. The thickness of the boundary layer, as you can see, that the boundary layer thickness increases with respect to x. So therefore you have it says, or in fact there's no need. In asymptotic methods, there's no need to put the square root. The square root of order of square root of x times epsilon is the same as order of x times epsilon. So I don't need to put the square root, but I did put it there. Okay. So that's the growth of the boundary layer. So you can see that the thickness of the boundary layer grows with respect to x, and also depends on the value of epsilon. And epsilon, as you know, is 1 over the Reynolds number. So therefore, the higher the value of the Reynolds number, smaller is the thickness of this quantity of the boundary layer. Okay. Now, so the outer flow is clear. So this is the outer flow, and then from Euler's equation, one can show that everywhere in the outer flow, the velocity is 1. Okay. So as I indicated before, so now we need to rescale this equation, and rescale this equation in such a form that the epsilon no longer appears here. And one such scaling is given by this. For example, if I define an independent variable eta in this particular form, okay, and postulate a function f, which is given by this expression, it turns out that you can actually, in terms of this independent variable eta, this particular equation can be transformed to this form, which is the Laplace's equation. I just want to quickly illustrate how that's done. For example, if you, okay, so here you have this quantity eta. You have this quantity eta, which is y times over square root of x times epsilon. So one thing you notice in this independent variable, that see close to the, in this boundary layer, the value of y is small in this quad because the boundary layer is 10. So now, if it's scaled, since we have said that epsilon is small as well, if you scale it by this as the square root of epsilon, then you can see this eta is now a quantity of order unity. So that's the scaling. So epsilon is small, y is small, but the ratio here, it turns out, is a quantity of order 1. So that illustrates how the scalings are done. So you want to rescale the problem such that everything is of order unity. Now you can rewrite this equation if you take the derivative d eta dx, which is minus eta over 2x. You can readily show that. D eta dy is 1 over square root of epsilon times x times epsilon. Maybe I should, okay, so define the stream function psi, which is some quantity f of eta times square root of x times epsilon, okay? So then the u component of the flow velocity is going to be dc dy. So you can readily show that if you differentiate that expression, you get an f prime, and this is square root of x times epsilon here, and then d eta dy is 1 over square root of x times epsilon. So you can see that u is f prime eta. You get that, okay? So that's u, and the v component of the flow velocity, v component v, of course, you can derive that as d psi dx. You can you can get d psi dx. So which is now you need to differentiate that expression. So therefore, if you do, so this is going to be f of f by 2. It's going to be 2x square root of x times epsilon. That's what that is. Then the second term is going to be f prime square root of x times epsilon, or eta over 2x. So you can see that the v component of the flow velocity is actually, I'll put a minus sign here, so minus v. So you can see that it is 1 over 2 times, okay, it's I made a mistake here. Eta, okay, eta is, yeah. So it's, okay, this is, sorry, no, I'm sorry, this epsilon goes in the numerator. I'm sorry, I made a mistake. Epsilon goes in the numerator. So it's, yeah, epsilon goes in. Okay, the epsilon actually goes in the numerator here. Okay, so that's this is square root of epsilon here, right? So this is square root of x. So you can notice that this is a square root of x, and there's an epsilon square root of epsilon in the numerator. So this is f minus eta f prime. So you can see that immediately. You can see that the v component of the flow velocity is of the order of square root of epsilon. So v component of the flow velocity is small. Okay, and it's of the order of square root of epsilon. So if you continue this, one can actually obtain an equation, ordinary. So from the partial differential equation, one can actually derive an ordinary differential equation. And what you notice in this ordinary differential equation is that the parameter epsilon no longer appears. So now it's possible to integrate that equation. So once you integrate the equation, once obtains f as a function of eta, then one can obtain the velocity profiles from that, velocity profile u as well as u as well as v, and then once you get the velocity profiles, one can obtain the drag. So here you can see this is an illustration of how asymptotic methods is used in a typical classical problem in fluid mechanics. Yeah. Yeah. No, that's not what I said. We have selected the scalings, okay, such that we looked at it, selected the scaling such that u is of order unity. Okay, so the way one does that, since you did ask the questions, I'm going to go back and to this. So here's the problem. I mean, what one does is, I mean, the momentum equation looks something like this. Okay, okay, and so basically, I mean, that's all you start with. I mean, that's the momentum conservation equation. Oh, it didn't show up here. Oh, good. Okay. Okay. So that's so you can see that's the momentum conservation equation, correct? So we have selected u such that this is already of order unity, because we said that you non-dimensionalized u with respect to the free stream velocity. So you can see that here u is already of order unity. Okay, so that's momentum conservation. So now the question is, how do you select the length scale L? Okay, there's a length scale that appears in the problem, and the length scale is selected such that the derivative. So you select a length scale L such that this derivative du dx is also of order unity. So that's the way it is done. Okay? So now the velocity scale is selected such that u is of order 1, and the length scale is selected such that du dx is of order 1. Okay? So that lets you select the length scale as well. So then you apply, then one can go back to the mass conservation equation, which is du dx plus dv dy equals 0. And then from here, you see, since du dx is of order unity, since you've already selected the length scale, then it implies that dv dy must be of order unity as well. Okay, that's why the equations are balanced. Okay, so then one can then of course one can conclude that the gradient, for example, you can say that d by dy is of order delta. So that implies that so d of y is 1 over delta. It's delta minus. Is 1 over delta. And that implies, since d by dy is order 1 over delta, v should be of the order of delta. So in that case, if you select it, so that makes this dv dy also of order delta here. Okay. Then you make an order of magnitude analysis in this particular equation. Then you'll see that because we have said that d by dy is of order 1 over delta, which is the thickness of the boundary layer. So therefore, there's a delta squared that appears here, because that's of the order 1 over delta squared, and that's of the order unity. So you see, this is of order unity. This is of the order delta squared, 1 over delta squared. So therefore, to force the second derivative terms back into the equation, it requires that epsilon over delta squared must be of order 1. Okay, so that's the. I don't know if that answers your question. That's the way it goes. Yeah.
Top right side where you have written the momentum equation.
Yeah.
The epsilon is a non-dimensional number.
What's that?
Epsilon is a non-dimensional
Yes.
number. So you will get only after we scale the x and else we should have mu by rho or something like that.
But so is everything. So is u and so is y.
So
Everything.
they are scaled.
They're all scaled, yeah. Yeah, these are all non-dimensional equations. There are no dimensional equations here. They're all non-dimensional. Okay. All right. So that's okay. In fact, I mean, I'm glad you asked this question. So I can see that because, so as I pointed out, this particular term here, d squared u dy squared, is of the order 1 over delta squared, and everything on the left-hand side is of order u. This is of order unity, and this is of the order 1 over. This is of order 1. This is of the order 1 over delta squared. Okay. So now, since we do need, since the u component of our flow velocity has to satisfy two boundary conditions, right? One at the surface of the plate where u is 0, and at the free stream where u is 1. So therefore, it's necessary to keep this term in the equation. So in order to keep this term in this equation, we have to have the constraint that epsilon over here, the epsilon over delta squared must be of order u1. Okay, it's necessary for that. So therefore, the boundary layer theory tells you, this is where the boundary layer theory tells you that the thickness of the boundary layer is of the order of the square root of epsilon, and that's the important point. Okay, so when I had written down the expansion for epsilon, okay, when I written down the thickness of the boundary layer here, it's because I was anticipating this result. Okay, so this was actually written based on this argument here. Okay, all right. Okay, that makes sense. All right. Okay, so that's the asymptotic theory application of asymptotic. So what did we learn? What we learned was, by application of the asymptotic theory, it told us a very important thing. And an important thing is that the thickness of the boundary layer must be of the order of the square root of 1 over the square root of Reynolds number. And that's important. They came from asymptotic theory. It was not postulated, okay? And let's, as far as the simplifications to the equations are concerned, there's numerous simplifications. You see, we started out with an equation with a second order derivative of u and x. So therefore, but now the order of the equation is reduced. So now it's only first order with respect to x. So therefore, the equation now is parabolic in x. So and that's an enormous simplification. The equations are parabolic in x rather than what previously it was actually, it had to satisfy two boundary conditions. Now it has to satisfy only one condition. So that's a major simplification. And now the second derivative term is also dropped. All right. Okay. Okay. Now here I want to quickly illustrate the use of asymptotic theory in heat transfer. Now again, this is the energy conservation equation written in the non-dimensional. So again, these are all scaled. Okay. So that's the energy conservation equation. And now in here, let's look at the non-dimensional parameters that appear. The non-dimensional parameter that appears is the, so this is actually defined that as epsilon, 1 over Reynolds number, Prandtl number that appears here. There's another interesting quantity, the Eckert number. The Eckert number is given here. Okay, so it's actually, is the ratio of the kinetic energy or the thermal energy in the denominator. That's what the kinetic energy or the thermal energy. That's the Eckert number. And this product Reynolds number times Prandtl number is defined as the Peclet number. So, and here's the Prandtl number again is a property of the fluid because only properties appear: viscosity, heat capacity, thermal conductivity. So therefore, this is a property of the fluid. Okay, now if you look at this Eckert number, you can see that the Eckert number is actually proportional to the Mach number, and one can actually quickly illustrate that as well. Okay, how do you do the other page? Good. Okay. Oh, good. There you go. And I can go back to the previous one as well?
Yeah, sure.
Oh, that's great. Okay, so now you can see that the Eckert number is u infinity. Oops. I don't want that color. Okay, u infinity squared over Cp delta T ref. Okay, infinity delta T ref. So that's the Eckert number. You can So as you can see that for the perfect gas, one can show so you have Cp equals Cv plus R. So if you divide that, so therefore you can get, if you divide that by Cv, so you get Cp minus Cv equals R. So 1 minus 1 by gamma, which is the ratio of the specific heats, or R over Cp. You can see that is gamma minus 1 by gamma, is R over Cp. So for this particular term here, it will be U infinity squared. And then C1 over Cp, therefore, it's gamma minus 1 over gamma R. So I'm going to multiply the numerator and denominator by T infinity. You get delta T ref. So for this, as you know, is the speed of sound. The speed of sound A is square root of gamma RT. Therefore, this turns out to be the Mach number squared times gamma minus 1 T infinity over delta T ref. Okay, so the Eckert number that appears here is a function of the Mach number. So these are the parameters. The parameters that appear are the Eckert number, the Prandtl number, and of course the Reynolds number from the mass conservation, from the momentum conservation equation. Okay, so all the variables are scaled such as for example, theta, you could scale theta as which I didn't write it here. The theta, of course, that appears here is theta is the temperature T over some reference temperature over delta T ref. So we have selected the reference temperature as well as the temperature delta T ref such that theta is of order unity. So therefore, now a number of simplifications appear. You can see immediately some simplifications that appear. For example, if the Mach number is very small, which is a low speed flow, then this Eckert number completely drops. So this term for low speed flow just drops. So when this drops, you can see simultaneously this term drops as well as that term. Now this, I mean, I'm not showing you that, but this viscous dissipation phi is of the order 1 over delta, is of the order 1 over delta squared. Is of order 1 over delta squared. And as we have previously shown, that Reynolds number times 1 over delta squared is for order unity. So phi v divided by this quantity, all this stuff is of order unity. Okay. So now for small Eckert number, you can immediately see that all these. So you have several terms that drop this, this, and this. So it's the problem is very, very simple now. It's only convection and heat conduction. That's the classical problem that you get. Okay. Right. Okay. So I think I should go a little faster. Okay. So for constant properties, so for low speed flow, this is the energy conservation that equation that appears. So now the thickness of the boundary layer, just like what we had before, the thickness of previously we had this quantity epsilon, so the thermal boundary layer thickness here is going to be, previously delta was x times epsilon, the thermal boundary layer thickness now is x times epsilon over the Prandtl number. So that's the thickness of the thermal boundary layer that appears. Okay, now you can readily show that, because again with delta was of the order of x times epsilon. So now you can see that the ratio of delta. Better write that. Okay, yeah, there it is. Yeah, the delta. If we take the ratio of these two quantities, you can see that the Prandtl number is the ratio of the boundary layer thickness, the thermal boundary layer thickness, or I'm sorry, the momentum boundary layer thickness over the thermal boundary layer thickness. Okay. And also, this is the Prandtl number is also the ratio of the kinematic viscosity to the thermal diffusivity. Now again, you can see another two sets of simplifications appear. Now this is the so-called distinguished, I'm going to apply what's known as a distinguished limit. What a distinguished limit implies is the following. So this quantity, we have already assumed that epsilon is small because it's a large Reynolds number flow. There's a Prandtl number that appears in the denominator. You're going to apply the limit that epsilon times Prandtl number is small. Okay, so that's that limit. But then I can look at the Prandtl number and can say either the Prandtl number is very large or the Prandtl number is very small. So this is the classical distinguished limit. But this is small, but this Prandtl number in the denominator can either be large or small. Even if it is very small, still this. So that means the Prandtl number, still this limit is maintained. Okay, so this and one of these limits. Okay, so now, so let's take the problem is very simple. If you assume that the Prandtl number is very small, okay, so that implies that the momentum boundary layer thickness is much less than delta t. So now maybe I should just go. Okay, here we go. So now so this is let's say that's the thermal boundary layer thickness delta t. This is for small, so this is for small Prandtl number, which are liquid. As I said, Prandtl number is a kinematic viscosity over the thermal diffusivity. So that's a liquid metal where the thermal diffusivity is much larger than the kinematic viscosity. So now you get the velocity profile. So let me just so this is the thermal boundary layer thickness, and this is delta t, and delta looks like this, very small. Okay. Now if you draw the temperature profile, let's say that's the temperature profile. Okay. Now you notice that in the majority of the thermal boundary layer, because this is so small in comparison to the majority of the thermal boundary layer, one can make the approximation that u is 1, the velocity is unit. Okay. So if you make that approximation that u is 1, which is this quantity here, then this problem reduces to a very simple problem. Okay, it's a heat conduction solid. I'm sorry, this must be a theta. Okay, there's a typo over here. This is a simple heat conduction problem, basically. Okay, this is the classical transient heat conduction problem. In transient heat conduction problem, that's going to be the time that appears. Okay, so now you can define another variable eta, which is given by this term, and now you can see that then you get an ordinary differential equation. And the solution to the ordinary differential equation is the simple error function, the classical the complementary error function that appears. So here you can see that. So we made two approximations. We said that Eckert number is small. We got rid of most of the terms, and we said Prandtl number is small as well, and we got the temperature profile. Okay, so that's the power of the asymptotic method. Okay, now once you do that, then one can get the Nusselt's number, which is given by that expression. So it's quite straightforward. Okay, so again, these approximations make a very difficult problem into a classical heat conduction problem. Okay, now let's look at the other limit, where the Prandtl number is very large. Okay, which are viscous oils. So that Prandtl number very large means it's just simply the opposite. The hydrodynamic boundary layer thickness is much larger than the thermal boundary layer thickness. So that's basically it's simply the other one. For example, this is the hydrodynamic boundary layer thickness. So this is, let's say, delta t, and this is delta over here. So now you can see that when you draw the temperature profile, so if you draw the velocity profile, it looks something like this. Okay. Now the thermal boundary layer is over here. That's the temperature profile. Now you can see that the majority of the thermal boundary layer, one can make a linear approximation for the velocity. One can assume that the velocity profile is linear. That's the thermal boundary layer. So when you make that approximation, again you can get analytical solutions to the problem in that limit where the velocity profile is linear. For example, that just comes from du dy. Okay. Okay, so I don't know what I did here. So anyway, we'll write here. So simply say du dy is this tau, the shear stress tau. So therefore here you can, at the wall of course. So now you can see that u is actually is the tau w, y over mu. So one can get a linear approximation for the velocity profile written that particular. So once you make that approximation, again one can get analytical solutions, and it turns out that analytical solutions one can obtain in terms of the incomplete gamma functions. So then one can obtain the Nusselt's number as well. So that's the power of the asymptotic technique. By making some very simple approximations, we're able to get the heat transfer. Okay. Okay, I'm going to move on. Do you have any questions on this so far? Yeah.
So that Prandtl number expression, delta y delta t, this is applicable every case, right? Not only for flat rate, right?
Which one?
Prandtl number is approximately delta by delta T.
Wait, that's valid for all. That's correct. Yes, it's not particular. Yeah, it's always valid. Yeah. Now the point is that the Prandtl. I mean, this is always true. I mean, the Prandtl number as being the ratio of these two quantities, except they are looking at the asymptotic limits of small Prandtl number and large Prandtl number. Okay. All right.
If there is a flow of hot gas on a flat plate,
Yeah.
thermal boundary profile will see.
Yes. Yeah. When you're talking about a hot flow, basically you're saying that the yeah, you could have it doesn't. Okay, let me change on the page here. Oh, there you go. Another page. Okay. So the question was, this is the. So this is so now the flow comes in this direction. Okay. Then you have u equals what? U equals 1. And of course, let me just let's just use dimensional way. Okay, that's U infinity. T is equals T infinity, and the wall temperature, let's say, is T wall. Okay, so this is T wall. So the idea is that if you have a hot flow, if the flow is hot, it simply implies that T infinity is greater than T wall, right? Okay. Or you can have when you have a cold, when you have the wall is hot, then you have T wall equals T infinity. So what I have shown you today applies to both cases, because it's all taken into account because we are taking this theta, which I simply said that was T over T infinity, for example, delta T ref. The delta T ref, I can write this as T wall minus T infinity. So it doesn't really matter, whether the fluid is hot or the plate is hot. This analysis holds for both. Okay. Any other questions? All right. So now I'm going to move on to, since we spent quite a bit of time on the classical the heat transfer fluid mechanics. So now I'm going to look at a problem which Professor Ramsey looked at yesterday also, and that is the problem of thermal explosion. This again is taken from Foreman-Williams' book on the entire thing is taken from Foreman-Williams' book in the combustion theory. Okay. So here you have a vessel. The volume of the vessel is V. That's the surface area. S is the surface area. And T, this is the wall temperature. T wall is maintained at some temperature, T wall. Okay. And then some reactants flow into this vessel. Okay. And we're looking at so now we're looking at the combustion process that takes place inside the vessel. So again, it's homogeneous mixture, and there's no flow. Okay. So that's a non-flow system. All right. So now we will assume that the chemical reaction takes place by a one-step process of reactants going to products. Okay? And the molar rate of consumption of so let's say what enters into the reactor is a mixture of the fuel and air, and the molar rate of consumption of the fuel is given by this expression, where W is the reaction rate, so the molar rate of fuel consumption per unit volume per second. This is the CFU is the initial concentration of the fuel that enters. Okay, so that's CFU. U always implying the initial concentration. B is the frequency factor of the reaction. Okay, this quantity phi is the ratio of the concentration of the fuel that is here. At any time, that's the instantaneous concentration of the fuel. So this has been non-dimensionalized with respect to the initial concentration. So you can see that immediately by selection here, by this particular selection of CFU, I've already made this quantity phi a water unity here. Okay? E over R, E is the activation energy, R is the gas constant, T is the temperature. Right. Okay. And now one can write now very quickly write the species balance equation. That's for the balance equation for the fuel. I can see, as I said, this is only there's no spatial derivative, so the change in the mass mole fraction of the concentration of the fuel, the volume, is given by this expression here on the right hand side. Okay, with a negative term. And the energy balance is given by this equation. So now the energy balance has you have this. This is the chemical reaction term. That's the change in temperature with respect to time. and then you have this, the heat. So this is the heat loss to this. So the idea is that there's some heat loss to the surroundings here. There's some heat loss to the surroundings. Okay. Right. Okay. Now, so the boundary conditions for this equation are that at t equals 0, that phi is 1, and t is t wall. Okay, those are the boundary conditions that we apply. Okay. Initial conditions. Now the next question is how to non-dimensionalize the set of equations. Okay. Maybe I should take a lot of time, but I'm not sure. Okay. Okay. So that particular equation, for example, you can write that as a. See, one important point here is that we need all terms in this equation. We need the heat. We need the source term. We also want to know. We also need to retain this particular term in the equation as well, because we are looking at the critical conditions of ignition. So we want everything here to be of order unity in this equation. Okay. So one way to do that. So now the question is how do I select the time scales as well as time scale in this problem? One way to select the time scale is, for example, if you simply write rho CV. Okay, times v, and you divide by this one here. You divide by h times s. Okay, and then you have dt, dt, and you have this entire term, whatever term there is divided by 1 over h times s. Okay, and then you have t minus t wall. Okay, so now you can immediately see that. Since I want to retain this term in the equation. So I can, if I select a characteristic time, which is actually which is a rho CV over h times c. If you select a characteristic time in this particular fashion, okay, then we are able to keep that term in the equation. Okay, so that's typically what's done here. You can see that now that's the characteristic. That's what's here. That's the characteristic cooling time. And then the analysis is going to be done for large values of the activation energy. Okay, so therefore now the epsilon is defined by this. See, E by R is large. Activation energy is large. That's the wall temperature. So therefore, for large values of the activation temperature, this quantity epsilon will automatically be very small. Okay, so now I have defined this tau by this expression, tau over Tc. If you look at this term on the right-hand side, you can see that, okay, again, now why does this epsilon appear in the denominator? The reason why it appears in the denominator is that only for a small temperature rise, ignition will take place. Okay, so you start up with T wall, and if you have a small temperature rise, ignition should take place. So therefore the theta will be will be very small. Okay, so theta will be small had I not put this epsilon in the denominator. Okay, by putting the quantity epsilon in the denominator, that forces this quantity theta also to be of order unity. Okay, so now that's the once one does that, okay, and then there is this gamma. There's a term that gamma that appears. Okay, now if I write this equation, okay, it takes this particular form. Okay, now remember that so that this delta here is actually this. Okay, here. Now here is again, but now in this particular equation we must have delta of order unity. Otherwise, if delta is not, if this is of order unity, and if delta is not of order unity, we cannot retain that term. So immediately this suggests that the delta must be of order 1. Okay. So now we have. So that's the equation. So that's the equation that you get, the energy balance equation. All terms are of order unity now, except this. Okay, and that's the balance equation for the fuel. So what we have done is forced all terms in the energy balance equation to be of order 1. And as a consequence of that, what has happened is if you look at the species balance equation, this term epsilon gamma appears. We have already said that epsilon is small. Okay, so by forcing this to be of order 1. Epsilon has appeared here. So now since we have said epsilon is 1, so from in the asymptotic analysis, we can simply drop that term, the entire term on the right-hand side. Okay, so that means the solution to that equation is simply phi equals 1 everywhere. Okay, so that's the leading order solution to that problem. Okay, all right. So now I can put phi equals 1, and we can look at that particular equation. Okay, so now, so now you can divide this delta, put this delta on this side, okay? So now, okay. So that's the equation that you get. Okay, so it's d theta d tau 1 over delta. That's the source term, and that's one of the cases. So this is the equation that results. Again, from an asymptotic approximation, we have shown that phi must be a Porter unity. Okay. Now you can see that. Okay, now we can plot this. You can see that this is the exponential e to the power of theta. You can see that's the plot over here. Okay, so what I'm plotting is the temperature difference versus this term and that term. Okay, so you can see that as the source term goes like this. That's the source term. Okay, that's exponential theta. Now you can notice that as theta becomes very large, okay, if you look at this, as theta becomes very large, see, the idea is I can drop this term in comparison to this only because epsilon is small and theta is a order unity. When theta becomes large, then one can actually drop this, okay? So therefore this is actually 1 over x exponential of 1 over epsilon. So therefore you can see that this particular curve starts out like this, and then it turns around because it turns around that way because for large theta. Okay, so that's the heat generation term. Okay, now this particular quantity here, theta over delta, is the heat loss term. So you can see that for different values of delta, as you increase delta, you get different the slope decreases as delta increases. So this is the increasing value of delta. And again, Professor Ranzik talked about this X-ray. Then you have a criticality condition. So this is so the intersection of this heat loss term and the heat generation term. That's where the system reaches steady state. Now you can see that the criticality will define the thermal explosion. Okay. So now at the criticality condition, two conditions must be satisfied. Exponential theta must be equal to theta over delta, and the slopes, to both the slopes and the values must agree. Okay. So if you make that, if you let the slopes and if you let the slope and the value agree, okay. So that's the slope, and that's the value. So now if you solve these two equations, you find that, so you get the following solution, that the solution is theta is 1, delta equals 1 over epsilon. So you can immediately see from asymptotic methods, we have been able to derive the value of delta at which at the criticality. Okay, so again, I want to point out that delta is, this is delta. So delta equals 1. If you put that equal to 1, you can calculate it. You can obtain the value of the T wall, for example, at which the system will ignite. Okay, right here. Okay, now let's say now let's consider another interesting case where now I want to consider a case where delta is very large. Large values of delta implies that so this is very large. So large values of delta, okay. So which is this, for example, okay. So that system is ignited, okay. So now we can consider what happens. We can look at the ignition delay time for large values of delta. So that's what we're looking at here, okay. So you put large values of delta. Then of course when delta is large, if you look at this particular equation, you can drop that term, okay, for large delta. So you only have a balance between this and this. That's the balance, right? So now that's what it is. Okay, sorry. Okay. So that's that equation, okay? So now you can define a tau. Again, this is a stretched variable tau. You can see that that's delta is very large, okay? Then the tau, so the ignition, so as delta gets larger and larger, the ignition delay time decreases, right? So therefore, so now this is very small, tau is going to be small, delta is large. So you define a new independent variable tau hat. So that makes tau hat a Porter unity. So therefore you get that particular equation, okay? The initial condition is being tau equals 0 at theta equals 0. One can obtain a solution to this equation, and that's this that's the equation. That's the temperature of theta, okay? And now the ignition delay time is defined. For example, when theta blows up, okay, the theta becomes exponential, becomes very large, and that will happen when you put tau hat equals 1, okay. So So that's tau height equals 1, that's when theta, you have a blow off, okay? So therefore now you can get an expression for the ignition delay time. So what we have, so the two things from asymptotic methods we have derived analytically, the criticality condition, and also we have obtained an expression for the ignition delay time, okay? All right. Okay. So should I continue, or maybe that's just, maybe I can. Okay. Yeah. Maybe. Okay. So that's but. Okay. Sure. Okay. But this problem will take quite some time. The one I want to discuss next. Okay. Okay. Now this is again. This problem Elijah talked about yesterday. And this is the previous problem that we looked at was actually a non-thermal ignition. I'm sorry, that the previous one I looked at was thermal ignition. The ignition was due to heat loss, balance between heat loss and heat generation. Okay, so what I'm going to look at right now is non-thermal ignition. Okay, so this is again the previous thing I took from Professor Williams' book. And this particular analysis that I'm going to talk about today was actually first derived by Norbert Peters in Aachen. So this is Peters' analysis of non-thermal ignition. Okay. So again, I said since Elijah has talked about this in detail yesterday, so I'm going to very quickly go through that. This is we're looking at hydrogen-oxygen system. Okay. And here the ignition is due to competition between chain branching reactions and chain termination reactions. Okay. All right. Now, so now one can write the kinetics is as follows, right? That's the Professor Ramsey as Professor Ramsey pointed out. That's the most important reaction in combustion theory. The chain branching step H plus O2 going to OH plus O. Okay, and these are the two shuffle reactions that appears, right? So both these reactions are very fast. So what that implies is that it very rapidly goes in the forward as well as in the backward direction. Okay. So very often one can introduce what's known as partial equilibrium approximations for these two reactions. Okay, that's the chain termination step. H plus O2 plus M going to HO2. HO2 is relatively inert in comparison to H radicals that terminates the chain, and this is the chain initiation. So the reaction starts with H2 plus O2 going to HO2 plus H. So now I want to show that if you take again, this goes back to derivation of reduced mechanisms. For example, if you take the H plus O2, H plus O2 reaction, okay, OH OH plus O, and you write down the other two separate reactions, which is H. I should not touch this here. H. H2 plus O is OH plus H. Now I'm going to take the last one, I'm going to multiply that by 2. So I'm going to write 2OH. Remember, these reactions are very fast. So 2H2 goes to 2H2O plus 2H. Okay. Now if you add all these reactions, okay, so again these are very fast reactions. So as soon as H attacks O2, forms OH and O, this O immediately goes here, attacks the H2 to form this, okay? And the OH that is formed in these two reaction steps immediately do that, right? So therefore, if you add them all up, you get that the net reaction is 3H2 plus O2 going to 2H plus H2O. So that's the net effect of, so this goes very fast. I'm sorry, this is not fast, so this is the rate limiting. As soon as the reaction happens, that goes immediately, and that goes immediately, and you add them all up, you get this net. So this is the net effect of these three reactions, okay? Now the question is, what is the rate of this particular reaction? The rate of this particular reaction, because that's we started from here, the rate for this particular reaction must be a rate of this elementary step, okay? So the rate of this, so the rate at which this reaction proceeds, the rate constant of that reaction is simply, if I take W1 for example, the rate, okay, the rate constant of the reaction is simply the rate constant of this particular reaction is the rate constant of this, which is K1. Okay, so right? So now we have only 3 reactions to consider. We have this global step, which is the chain branching step, the chain termination step, which is here, and that's the initiation step, okay? Now let's look at some other simplifications that appears here, okay? Well, if you look at the heat release, right? The heat release, the enthalpy change of this reaction, of reaction 1, the enthalpy change is like 48 kilojoules. Step 4 is actually slightly endothermic, so that's it's not the enthalpy negative. This is negative of the enthalpy change, okay? So therefore this is exothermic, slightly exothermic. This is some slightly endothermic. Now it turns out that most of the heat release takes place in this particular reaction here. Okay, for the here, of course, the negative of the enthalpy change is a 197. So when you write down the energy conservation equation, it is sufficient only to consider the contribution of this particular reaction. We can neglect the contribution of the chain branching step as well as the initiation step in writing the energy conservation equation. Okay, all right. So now let's write down. So that's the species balance equation, right? That appears written in terms of the mass fraction. So that's mass. So y is the mass fraction of h, all right? And then you can see that the h. So there's a 2 times w1 that comes from here. Okay, that's the rate wr1 being the rate constant of that particular comes from the rate constant of that reaction. W4 is the initiation step, and W5 is the chain break, the chain breaking step, which is this. Okay, right. All right. Okay. So now, as far as the energy conservation equation is concerned, I need only to consider the contribution of step 5, because the contribution of the other steps are very small. Okay. Right. Now let's take this case where the initial mass fraction of hydrogen, oxygen, and the temperature. So this is the initial mass fraction of hydrogen, initial mass fraction of oxygen, and that's the initial temperature, okay? Now, so what's very important, it's a very crucial importance. What's important here is that this particular reaction, this quantity m here, is the third body, okay? So if you write down the rate constant of this particular step, actually, K5, for example, okay, K5 will be equal to C of H, C of O2, and then, sorry, this is the reaction, not K5, this is the reaction rate. W5, okay. Okay, so it's going to be the rate constant K5, all right? The CH, and the Cm that appear. So this is the concentration of the third body. The concentration of the third body, of course, it depends. So I'm going to write that as Z5P over RT. So you can see that the rate constant depends on the pressure. Okay, the higher the pressure, and this Z5 is the so-called catalytic efficiency. So it has different species have different catalytic efficiencies, and that's what that Z5 is. Okay, so that's all right. Okay, so that's what you see as C5. Okay, Z5 is the catalytic efficiency. So okay, so those are the two equations that we have. Right. And now, okay, now this is again this is from Norbert. What he has done here is compute to show how good this three-step reaction mechanism is. I talked about this three-step. Okay, this is the calculation of ignition delay time using a 17-step mechanism, which is a rather detailed mechanism. And then this is a calculation with an 8-step mechanism. I'm not sure what that 8-step is, but of importance to us today is this 3-step, the comparison of the 70-step mechanism with the 3-step. You can see that the 3-step mechanism very accurately reproduces the ignition delay time for hydrogen. These are numerical computations, okay? Okay, now what's important? What's important here is that if you look at the ignition delay time, so these are decreasing temperatures, as you see here, okay? Right? So what you see is that at particular, okay, yeah, yeah, you can see. So there does exist. You can see there's there's a rapid rise. Okay, here in this region, there's a rapid rise in ignition delay time, indicating that ignition is not taking place, and then you have something like that here. So there's a there does appear. Oh, here is 790. So there does appear that at this temperature 790, okay, we can define this. There does appear something like a crossover temperature, right? And this crossover temperature is such that if the temperature is below the crossover temperature, no ignition takes place. If the temperature is above the crossover temperature, then you get this. Okay, the ignition delay time decreases. So there is this crossover temperature that appears. Okay, let's see if we can obtain that from asymptotic analysis, that crossover temperature. Right. Okay. So now again we need to make this approximation that before ignition the temperature rise is very small. Okay. Because the temperature rise is small, you can define a quantity x, which is given by this expression, right? YH is the mass fraction of H, is normalized by division. So this is the initiation reaction, okay? So, and T naught is the temperature, the initial temperature. So all rate constants are evaluated at the initial temperature, okay? And now you define a characteristic time. Now the characteristic time, a tau, this is the time. Now the characteristic, so this K1 T naught, okay, so this is the rate constant of the chain branching step, H plus O2, okay? So now the tau is non-dimensional, so actually K1 is 1 over time, so therefore what appears in the denominator is the time, and that time that appears in the denominator here, that appears from K1, is the characteristic time for reaction 1 to take place, the chain branching step, okay? So it's non-dimensional, so the non-dimensional time that we have, the chemical time that we have taken is the chemical time for the reaction H plus O2, all right? So that's what, and this quantity kappa plays a very important role. So this is the ratio. You can see that is the chain termination step, H plus O2 plus M, and the rate constant of that's the entire thing. Here's, and that's it. So this is time derivative, okay? Chain breaking, chain branching, then there you have the initiation, all right? Okay, so those are the various terms in that equation, all right? Now initial conditions are at x equals 0, tau equals 0. That's the initial condition. Now it turns out that you can get analytical expression for that equation. You can solve that equation, okay? And that's the solution to that equation. You get the radical x, radical concentration is, you get a closed form solution for the radical x, okay, in terms of this. And now we have to look at this equation. I mean, this particular term, that's a radical concentration. Now you can look at what happens to kappa. If for example, if kappa is greater, if the value of kappa is greater than 2, okay, let's assume that kappa is greater than 2. If kappa is greater than 2, then you can see that this becomes negative here, right? So therefore therefore there is a solution to that. So you get a solution to that equation. Okay, so now what happens if kappa is less than 2? If kappa is less than 2, then you can see that x will increase exponentially. Okay, all right? There's an exponential increase in x. All right? So for kappa less than 2, there's an exponential increase in x. For kappa greater than 2, it will actually reach a steady state value. Okay, and then for kappa equals 2, again there's a steady state value because one can use L'Hopital's rule for kappa equals 2 and get an expression for tau, that expression for x. Okay. So let's look at that. Okay. Now here you have these various solutions. For example, as I said, that's the value of x. Okay. Now you can see that when kappa is less than 2, you can see that's how the radical concentration increases, and it's an exponential increase with respect to tau for kappa less than 2. Now for kappa greater than 2, it does that. Okay, it's because you can see that when so you can see as kappa is greater than 2, for very large values of tau, okay, it reaches this particular for very, very large values of tau, since kappa exponential disappears, correct? For large values, again, I'm looking at kappa greater than 2, this exponential disappears because it's exponentially small. You just get -1 over this quantity, so therefore you can see that reaches a steady state value here, okay? And this value here is kappa minus 2 to the power of -1, okay? And now what happens at kappa equals 2? At kappa equals 2, we can actually use L'Hopital's rule, okay, for this, right? You differentiate the numerator and the denominator, and then you, so if you do that, it's very straightforward. I mean, you can see that if you differentiate the denominator, you get a -1 in the denominator. Differentiate the numerator, you get you're going to get tau that appears, okay, just simply a tau. You put kappa equals 2, so therefore that's a straight line. So you can see that this kappa equals 2 is the boundary between when the explosion will take place, when the explosion will not take place, because that's the boundary. Okay. All right. So now, so essentially what's done is now if you put kappa equals 2, now if you look at the value of kappa, or here it is. Okay. This is kappa equals 2 gives this particular expression. In this expression, the crossover temperature Tc appears. Okay. So one can calculate for given value of the pressure. You can actually calculate the crossover temperature. Okay, so now these are plots. For example, there's the classical explosion curve, which Alicia talked about yesterday. Okay, this was obtained from a detailed numerical scheme by Warnards. That particular expression. Now the expression for the crossover temperature, which is calculated from this equation, you can see that very accurately predicts the second explosion limit of the H2O2 system. Okay. Of course, it fails here because there's no. Of course, it will fail over there, but then nevertheless, in this region, the crossover temperature calculated from this particular equation, it's very closely again approximates the second. No, they're not. I mean, maybe they are. I don't know. I just taken from Stahl and Warnards. Yeah, they probably are experimental. Okay. Maybe that's numerical and that's experimental. It's possible, yeah. But I guess I wanted to just emphasize that asymptotic. Yeah. Yeah. Yes, it does. Yes. Yeah. Okay, so I think I'm going to stop here, right? There's another section which I'll continue on. Yeah. Okay. So, are there any questions? Because I think we have gone over. Yeah. I mean, are there any questions? Okay. Right, yeah. Yeah.
How are you to choose your values?
I think the way you do that is when you choose I'll show that later on when we do rate ratio asymptotics. If you have different time scales, all right, you just select the time scale which is either the largest or the smallest. Okay, doesn't matter. Okay, pick one select time scale, and then if you rewrite the equations with that, write the equation with that time scale, then there will appear a parameter. That particular parameter will be either large or small, depending on which time scale you selected. Then you can do an asymptotic analysis. There you can simply say, well, I'm going to assume that this drop that particular term, okay, whether the small term or the large parameter appears. Then you solve the rest of the equations. And that rest of the equation is valid for the other time scale that you looked at. Then you rescale the problem with the next time scale, then you get another solution, then you have to match the solutions between them.
For the mass conservation, you have assumed the volume to be a constant. Writing the governing equation for the thermal explosion, the mass conservation.
Okay, not this one right here. Oh, this one?
Yes.
Okay.
So the volume will also be a function of time. The volume inside the chamber because of the combustion.
No, the volume V that appears here is the entire, this volume. Okay, volume of the vessel. Okay, so that's the V that appears.
But is the explosion happening as a wavefront or all?
No, this is happening everywhere. It's uniform.
Okay.
So there's no. You see, this particular equation does not have a spatial derivative. Okay, so it's happening everywhere. Okay, so we are deliberately neglecting spatial derivatives.